Welcome back for the second part of this video where we look at thermally induced stress due to thermal expansion in a constrained bar using a 2D plane strain analysis. So we're just going to look at the results of this analysis just to go over I'll recap how we set the analysis up. So we created the 2D geometry and we set our geometry to generalized plane strain, and the thickness of our bar is 1 inch in the Z direction. We're using stainless steel, and the global coordinate system is shown here at the lower left point of the rectangle. We used quadratic elements and meshed it to 1/8 of an inch size. And this bar is 5 inches long, and the cross section is 1 by 1. And we used displacements to set up symmetry. So this bar is only 1/2 an inch thick in this direction. Because of the plane of symmetry, it's 1 inch. And then we set up a compression only support on the right end so that the bar is constrained in the X direction and allowed to grow in the Y direction. And then for our thermal condition, we added 2 time points by changing the number of steps to 2. And one thing that I will mention is that in the previous video, I set 0 and 1 to 70. And I believe 0 needs to be kept at the reference temperature because that is referencing your coefficient of thermal expansion value. So to get my results to better match the hand calc, I had to leave that reference temperature. And then I set time step 1 equal to the reference temperature, and then added a 50-degree delta relative to the first time step. And then we post-processed our results. So you see here now I'm getting a compressive stress of negative 13,201 psi, and that equals our minimum principal stress because it's compressive, and also our equivalent stress because we only have one principal stress. See, our maximum is 0, as this is only a compressive stress. And then I've shown here our force reaction. So if we look at theory, pretty straightforward for a 2D bar that's constrained in the lengthwise direction. The strain is equal to the coefficient of thermal expansion times the temperature delta, and the stress is equal to negative alpha delta T times the modulus of elasticity. And I've shown here the calculations for the stainless steel material, and we get negative 13,211 psi. And that's pretty close to our result from ANSYS. All right, so yeah, thanks for watching, everybody, and I'm looking forward to comments or questions that you have, and I'll continue making videos on ANSYS tutorials for you. Thanks very much.